Okay, we're very happy to have Jonathan Heckman from UPenn to tell us about the top-down approach to categorical symmetry. Wow, take it away.
Should I put this on?
Oh yeah, sure.
Or do you need me to?
Yes.
So I put it on. See a faint light.
Yeah.
Test. Test.
Yeah.
Right. I assume it's for the people on Zoom. All right. Okay. So first, let me say thanks very much for the invitation to come visit and give a talk. Okay. I should also mention plus work in progress. The other thing is I should probably say that I think I looked at some of the talks that you have. This is probably going to be much more on the physics side than some of the other ones, but hopefully I'll be able to convey at least the spirit of what we're trying to do and how we're going about thinking about it. Okay, so what's this talk going to be about? So on the one hand, I'll be telling you about what I'll refer to as a top-down approach to making quantum field theories and constructing them and studying them. And by top-down, I mean we're going to be taking various limits within string theory, taking various limits to remove some of the degrees of freedom that come from string theory, such that we're left with a pure quantum field theory sector. And the idea is to use the geometrical starting point as a way to study some aspects of those quantum field theories. And so in some cases, it's going to be at the level that we don't even necessarily know how to characterize in kind of a more conventional textbook way what those quantum field theories are. Nevertheless, by writing down a geometry, we will be able to say some things about what those quantum field theories are. And on the other hand, I'll be referring to one of the ways that, or one of the main constraints we often have in physical systems. So one of the things we typically care about in physical systems is various kinds of symmetries, which can constrain the structure of the theory, the way that the operators interact with one another. And this has been recently become a very active topic in physics and also in certain areas in math, referred to as generalized, or maybe more fancy or pretentious name, categorical symmetries. And what I want to do is explain like how these two come together in this context. Okay, so to start, I need to tell you what I mean by quantum field theory. So, by the way, should I plan to run for about an hour or longer or shorter, or is it?
We're flexible. They usually go like 1 to 2 hours.
Okay, but 2 hours is the max. 2 hours is the max, and I should probably aim for closer to one. Okay. All right. So what we do is, what's our definition? And in general, I don't actually know the full definition, but what we can do is say, I know it when I see it, or I know how to give working examples. So we'll introduce a space-time and positions to label operators. So since we're talking about some quantum system, what we have in mind is some Hilbert space for the quantum field theory. And then we're imagining that we have various kinds of operators which act on that Hilbert space. So let me label one of them as something that is defined. So this is some viewed as some point in the space-time. I'll call this a local operator. And it acts on our Hilbert space in some way. So if you need an example of an operator that does this, in physical terms, you could say, I want to create an electron. I want to create an electron at this particular point in space and time. And I want to see what happens when I start scattering. Now, this is not the only kind of object that we can talk about, which might do something interesting when acting on the Hilbert space. So for example, we could also consider a so-called line operator, which doesn't have support on just a point, but rather might have some support on some line. And I really do mean some line that runs throughout the entire space-time, so some one-dimensional space. And again, it can act in some way on H. What would such a thing be?
So when you see a line, you mean the line running in time direction, but at a point in the space?
I mean, so when I say it like in a, so I want to create an electron at some particular point in space-time. That would be like the OX, like created at this particular point in space-time. So literally a point in like our 4-dimensional world or something like that. And then we could say, well, what if I didn't create that? What if it was an extended object of some kind? Maybe I want to create not an electron, but maybe I want to create some bigger extended object, maybe some heavy thing that extends out like this. That would be like a line. And if we're thinking about this at the level of what we might be doing in a quantum field theory, this might be like create a heavy string usually. So perhaps I don't orient the line like this, but maybe I orient it. Line is going to just mean some one-dimensional thing. It doesn't necessarily mean literally a line. It just means some one-dimensional thing. So this would be like a string. So it has one-dimensional support on where I've created it. Okay, so given such a collection of operators, and of course we can keep going, right? We could say, I want to tell you about local operators, line operators, things that are supported over 2-dimensional subspaces and so on. Now, now, what would you like to do as a physicist? So it goes. We'd like to compute correlation functions of various kinds. So if I give you a bunch of operators, they act in some way on the states. So a thing of interest might be to calculate something like this. So psi is some ray inside of the Hilbert space. I'm exploiting the fact that I have the inner product. I'm using the physics notation for saying that the operators are acting this way, and then I take the inner product with this one here. But this is the kind of thing we would like to calculate in many cases. And it may be point operators, it may be line operators, it may be more general things of interest. So there's a recipe available to us in some cases, not all cases, but in some cases, general cases. So the recipe is to introduce a so-called Lagrangian. Lagrangian and compute via Feynman diagrams. I'll give you an example in just a moment. So here's my example. And the recipe for calculating in the context of local operator correlation functions with respect to, say, the ground state. Something like this is to replace this by this formal thing that we manipulate as if we knew what we were doing in terms of the integral, but there's a formal technique for manipulating this. But we write down integral over the Lagrangian. Overall possible configurations of the field. And then we have this thing. And in practice, what this means is we do a perturbation series where we say, I'm going to write this thing in terms of the thing at lambda equals 0 plus the contribution perturbation theory in lambda. And so, for example, if we want to calculate a 4-point function amplitude, we would start with something like this and keep going. Just insert more and more things involving power series, basically in the parameter lambda. Okay. Have I lost you at this point? Or is it... Okay. So it's okay? All right. So what's one of the things that you can do already with symmetries? So even without like lifting the pencil, I can already tell you that if you gave me an odd number of these phi's, it's 0. And I can already tell you that if 2m plus 1 is like this, then this will be equal to 0. Now, how did I do that without actually evaluating anything? Well, it's because this integral that we're doing is, this part is Z2 even. So there's a symmetry of the problem. So there's a Z2 symmetry. And what it does at the level of the Lagrangian is it sends phi to minus phi. And we can clearly see that this thing is invariant under such a thing because everything is of even power in even degree in phi. So if I asked you for the correlation function involving this number of things, I could know right off the bat. Yes, exactly. So, yeah. So in this theory, yes, it is, and we know that this thing is 0. Okay, so this is kind of one of the kind of simple uses for a symmetry. You can just say, well, it constrained the correlation functions in this particular way. Okay, so that's very nice. That's a kind of old like textbook example. So I'll refer to this as kind of the way one proceeds in the context of a textbook quantum field theory. Yeah, at tree level it's 0, but if you include like all of the, if you start including loop correction, well, let's see. Yeah. Do I agree with you? Well, sorry, tree level, you could do something like this. Why? Okay. Yeah. Exactly. Yeah. So this has the phi cube. Yeah. Yeah. Okay. Okay. So. Yeah. Okay. So here's a general question we could ask. Great. If I want to characterize quantum field theories, perhaps all I have to do is tell you all possible fields of this kind and all possible Lagrangians that I can make out of those fields. So maybe if I was sufficiently powerful, I could just say, write down every possible field you can think of, write down all possible, things involving derivatives of the fields and polynomials and interactions in some way. Perhaps that characterizes every kind of quantum field theory we have. So here's a question. Do all quantum field theories come from, I'll put this in quotes, but perturbations of minus d phi squared. So this is in some sense the free field theory. This is the Gaussian fixed point we'd say, and we could say, well, why don't I just? Yeah. So you could also have something like, yeah, fine. It won't change the statement. You could say perturbations, things that are perturbations around free field theories. So general perturbations of minus half d phi squared, perturbations of this kind of thing, whatever you want to do, just at the level of free fields. We could make it more fancy, but that's the general question. Do they all come from things like this? Start with the free fields, perturb. This was of that kind, right? Because we started with lambda equals 0, and the machine we used was basically perturbation theory in lambda to even set up what we wanted to calculate. And the surprise, or one of the interesting things, is that there are examples that don't fit into that general picture. So in general, d greater than 4 quantum field theories, just as a general piece of lore, always appear to violate these considerations. There's general physical arguments for why that happens, because anytime you try to write down a Gaussian theory or a Gaussian fixed point, any perturbation you do drives you back to the free field theory at the long distance level. So what happens is you have to do something a little bit more involved. You have to be working very far away from the Gaussian fixed point to produce anything of interest. So examples. So here, what I mean by SCFT is super conformal field theory. So it's a theory that has a conformal symmetry. There's no mass scales or distance scales. That's what CFT means, and S just means it's one that has supersymmetry on top of all of that. I'll go through some of these examples a bit more, but just to explain like how these things come about at all, I'll just give you two examples. So in 6D CFT, an example would be the way we know how to engineer these things is basically only through string theory constructions. It's type 2B on an ADE singularity. So gamma is some finite subgroup inside of SU2. And this one comes from M theory on, so this is some 10-dimensional space-time with this particular background. So we're writing it as R 5,1 times this thing here. And then the other one would be R 4,1 times C3 mod gamma, where gamma SU3, gamma is some finite subgroup of SU3. So these things produce what we call 6D CFTs. They're interacting fixed points. They don't have the form of looking like this, of perturbation of some Gaussian field theory. They're more exotic. Similarly, if you pick the gamma correctly inside of here, inside of SU3, then you also get a similar thing. So the general lore is that D greater than 4 interacting QFT. You can, of course, do silly things like just write down a 5-dimensional theory with just the kinetic term. That's perfectly fine, but you won't get interactions at long distances. Are non-Lagrangian. And what this means in practice is, even if you could write down a Lagrangian, it would not be particularly helpful or useful. There would be no perturbation theory around the Gaussian fixed point. Perhaps there's a more exotic Lagrangian you could write down that doesn't start from 1/2 d phi squared or something like that, but it's not going to look like one of the conventional textbook things we've seen in 4 and 3 dimensions or 2 dimensions. They're going to be very far away from that. Okay, so these are some examples, and what I'm basically going to be telling you about is, okay, I'm going to first tell you how we build these things, and then how we start studying symmetries in these systems. So I don't even have a Lagrangian, so how could I tell you what the symmetries are that act upon states and operators in this setting? So the idea is to kind of characterize those kinds of symmetries using more of the geometry. So here I've clearly written down a particular background of geometry, and I'll be leveraging that to tell me about the symmetries. Yeah.
Question. So, way back in the decades ago, when we were working on topological theories, symmetries, and they were learning how to run. You know the wrong.
Correct. You don't. Indeed, it's that kind of philosophy. It's saying, in practice, if you want to really get down to it, if I want to tell you about like a 2D theory or something like that, I didn't really have to tell you Lagrangian at all. Really, all I have to tell you is the operators and the correlators. And that, in some sense, defines what I mean by the theory. It's a bit more challenging here because even the operator content is a little bit mysterious for these higher dimensional theories. But yeah, in practice, you don't need to talk about a Lagrangian at all. It's just, do you have a machine for calculating the correlation functions? In a topological field theory, for sure you do, in many cases. So at that level, yeah. So this is a little bit different from just a topological field theory, though, because it's got non-trivial spatial correlations that are much more challenging to characterize. But yeah, the philosophy is very much in line with what you're saying, that you don't really need a Lagrangian if you want to get down to the stripped down version of what you could mean by quantum field theory. Of course, if you have a Lagrangian, it's of course a very useful aid to figuring out what's going on. So, okay, I don't have a Lagrangian, so how am I possibly going to study this? So the idea is, this is what I mean by a top-down approach to building the quantum field theories. So we're going to be talking about string theory, M theory, maybe F theory. I'll only mention F theory near the end. On X, some non-compact background with localized singularities. It might also have, so the cleanest examples we can write down are, of course, just isolated singularities, but we also can entertain singularities that might stretch all the way out to, kind of the boundary of X. So the picture, the general geometric picture is, I'll typically assume that X takes the form of some cone. There'll be some singularity at the tip of the cone. That's where the quantum field theory is going to live. And then there could be additional singularities on top of those. So more singularities. These are more associated not so much with interacting degrees of freedom from the perspective of this quantum field theory here, but more what we refer to as different kinds of global symmetries. Yeah, so X is going, so yeah, good. So in this case, X would be C2 mod gamma in the 2B example, and X would be like C3 mod gamma. So in other words, there's a kind of a boring part where nothing is happening. That's just flat space or something like it. And then there's the place where there's the singularity taking. Yeah. So both of these have the same characterization. I can view them as cones. Yeah. Absolutely. So yeah, one of the other uses, you might say, why do you care about such a weird, set of field theories? Well, the point is that these also provide insight into many lower dimensional systems. So if you start with one of these 6-dimensional theories or 5-dimensional theories, by not putting it on 6 flat space-time dimensions or 5 flat space-time dimensions, but instead curling those up, compactifying further, you gain insight into 4-dimensional systems that are also non-Lagrangian in many cases. So if you start with these 6D theories, so instead, 6D on, say, R31 across Riemann surface of genus G, maybe with some marked point, you can wind up with many non-Lagrangian 4D theories, as Mina's already said. So in other words, again, these are, these look like exotic things, but they're happening all over the place from the perspective of this higher dimensional starting point. Sometimes you can also do deformations as you go down in the compactification, find a Lagrangian phase for the theory, and relate it to the non-Lagrangian description by varying the parameters to formally infinite values. So you can actually start connecting the non-Lagrangian with the Lagrangian world by kind of going to these regimes of extreme coupling. You can do that both for 5D. If you wanted to build interesting 3D theories, here's one way to do it. Just literally take the same thing. And there's all these different connections. So this would give you some 4D theory. This would give you some 3D theory. And I think you can figure out how to extrapolate beyond that. Okay, so these are just some examples of like non-Lagrangian theories that you can write down. And one of the things you might like to do is characterize what is going on in these systems. Probably just, okay, I'll use this board. Probably get into trouble though. Okay, so any other questions about this part? Okay, so I already mentioned that I'm going to do this through string theory or something like that. So I need to find some objects to play with to build you the degrees of freedom that I want to talk about. So this is probably a reminder for all of. No, I know. I know. Actually, you know what? Maybe I'll just put it on this little sideboard over here. So it'll just be a reminder of what I'm going to do throughout. So I'll mainly stick to 10 dimensions for type 2A and type 2B. But I will kind of mention at various points how M theory goes. But let's remember that in 10D, there's a type 2A theory and there's a type 2B theory that I can talk about. And there's 2 main players that I need to introduce here. There's going to be so-called DP branes. And so these things should be viewed as having P spatial directions in one time. So the world volume, if you like, it's filling out some P+1 dimensional subspace inside of your spacetime. So for example, a point particle, like an electron that moves forward in time, that would be a 0 brane of some kind. D is for the fact that it has corresponding Dirichlet boundary conditions from the perspective of an open string which ends on that thing. Okay, so now what are the supersymmetric objects, the stable objects I get to play with in 2A and 2B? Basically, I get to have P even in 2A and P odd in 2B. So in other words, the objects that I'm going to talk about are going to be things like D0, D2, D4, and D1, D3, D5. Now, an electron, for example, a point particle carries an electric charge. And how does that actually come about? It's coming about because in the space-time, we imagine that there's some one form well, there's some embedding of the time into our space-time. And then we can consider on the world volume of the electron, the pullback of this thing onto the world volume of the time. And this tells us directly that the electron can indeed be coupled to the one form. So similar to that, we have corresponding p form potential. We have corresponding p plus one form potentials, which couple to the world volume of each of these d branes. And this means, this is how we know that these things are stable, for example, they're carrying a charge. And so just like an electron cannot lose its charge, a d brane cannot lose its charge either. It's conserved throughout the way. So that's a stable object for us to speak about. So what I'm going to be doing is using these different kinds of d branes and asking, how do these d branes know about the singularities that we're localizing in that region over there? If we do that, then we'll have some evidence for what kind of theory we got. Do we actually produce an interacting theory, or did we produce something that was completely vacuous or empty at long distances? So I'll start with an example that's Lagrangian, in fact, but then I'll explain like the sense in which it, just by changing whether we're talking about 2A or 2B, we get to a non-Lagrangian example. So let's consider 2A on, okay, so our background will be, our 10-dimensional spacetime will be this, where the group action is just, so omega is just some primitive n through to unity. And so what we're going to do is we're just going to blow up the singularity as normal, and we'll get some collection of -2 curves. And what I'll do is I'll write down, so this is a helpful picture to draw in many cases. I'm going to be looking at what happens. So each one of these -2 curves is some P1 in the geometry. I'm going to consider what happens if I wrap a D2 brane over a P1. So apologies for the kind of funny notation, but P1 I'll fill out by locally with the 6, 7 directions, and 8, 9 will be the normal direction inside of, in this case, O-2 over P1. So this will be the normal direction. Let's imagine we wrap the D2 brane on such a thing. Okay, so what have we managed to do inside of this 6-dimensional spacetime? Well, what we managed to do is make a point particle. So this is a thing that's filling out time. So it's existing for a long time. It's a point particle and it's moving around. Now, it turns out that this point particle that we're talking about carries a charge. What is it charged under? Well, there's a dual 2 form we can talk about. So there's so in here we have a 3 form potential. That's the one. These 4 are associated with the C2 mod Zn. So if I look at the local neighborhood for O-2 over P1, then 6, 7 is like the P1 direction. So these are real directions. And then 8, 9 is just the normal locally. It's just a local picture. So obviously I cannot give you the same characterization, you know, for the entire chain of -2s, but that's the idea locally. They're just to visualize where did I put the D2. I wrapped it on the compact P1.
Okay, sure.
Okay, so in addition to this thing, we also have this 3 form potential, which is the analog again of saying the electron had a charge. It knows about, the electron knew about a 1 form potential. The D2 brane knows about a 3 form potential. And we can decompose that 3 form potential as a 1 form inside of R51. And then there's a normalizable 2 form, is dual to the P1 class. What is this thing going to descend to in 5D? Sorry, 6D. It looks like a 1 form in 6D. This is what we would refer to as some kind of charged state in the 6-dimensional theory. We've now built a charged state. It's a charged point particle, which is charged under this thing. Now, if you go through the whole exercise, what you discover is, in fact, this is building you in the limit where the P1s all contract to 0 size. in volume, what you're actually building is a 6-dimensional supersymmetric Yang-Mills theory with gauge algebra, SUM. That's just the Lie algebra for it. And literally the Cartan subalgebra is being built up from the reduction of these ones here. And then the, if you like, the off-diagonal elements of that Lie algebra are being built from the wrapped states associated with the D2 branes. So that's the SUN gauge theory. You could do a similar thing in M theory where you kind of lift it to one higher dimension, and instead of building 6-dimensional Yang-Mills theory, you build a 7-dimensional Yang-Mills theory. Any questions about that example? So yes.
The D2 brane, these are sub-manifold or contain some other information?
Oh, it contains usually more. So there's extra degrees of freedom. There's an additional quantum field theory that's usually localized on the P brane. But for what I'm talking about right now, the only thing I need to know is that it fills out a submanifold. That's a partial characterization of what it is. Yeah. Yeah.
So I know that the SUN part comes somehow from the intersection ones, right?
Correct. Yeah.
I just wonder how do you make it more concrete? So for example, for SU2 gauge theory, you have this trace F wedge star atom.
Yes.
But in the original C theory, you don't have this trace. Where does the trace part come from?
Oh, well, so one general way to argue that this must be the answer is to basically just do a thought experiment involving scattering amplitudes involving these things. And scattering amplitudes are enough to kind of constrain the form of like how different kinds of objects would bounce off of one another in this setting. So we can just say, well, I'm giving you a massless state, which is charged in some way under this Cartan in this way, right? It also carries a Lorentz quantum number, so I know it's a vector boson of some kind. That can all be worked out from working on the resolve phase. That is enough, just matching the scattering amplitudes, to say that at low energies, it must be characterized by a 6D non-abelian gauge theory of this kind. Now, what it doesn't tell you is there's trace F wedge star F. What about the higher order terms? That's not necessarily under control to the same degree by this kind of argument. All we know is that at leading order, it must be of this form. So basically, gauge invariance and scattering amplitudes is enough to kind of constrain the leading order bits.
What about directly reducing the Lagrangian?
Oh, yeah. So in this one, it's no problem at all because it's Lagrangian right from the start. Now there's a so remember what I said over here was 2B on C2 mod gamma, not 2A. So now if I do the same exercise for 2B, I'll get a very different looking answer for what's going to happen. So I'll do that right now, actually. So 2B will take exactly the same background at the level of the geometry. Okay, now the point is,
Previously, it's 60 super Yang-Mills with gauge group
SUN. Yeah, special unitary. And all I'm telling you here is actually the Lie algebra. Describing the global form actually requires me to pick boundary conditions off at infinity. So if I want to give you SUN as a group versus SUN, say, mod ZK, where K divides N, it all comes down to what I pick for the boundary conditions off at infinity in the C2 mod ZN. And I'll come to talk a little bit about that later, but that's why I'm trying to be a little bit looser with just telling you that for sure it's an SUN Lie algebra, but the group itself is dictated by a bit more.
Okay, so when you say the argument gives like a shrink this P1 to a point,
Yes.
and then you scatter this D2 branes and maybe have like particles charge.
Yes, that's right. And then that's enough to actually reconstruct that it must have been an SUN gauge theory at leading order. Now, what's not dictated by this is that there's loads of things you can add at like higher order in terms of gauge invariant operators. So it's not probably going to be just pure super Yang-Mills. I mean, there's like supersymmetric deformations you can switch on that are not they're not dictated by supersymmetry. So that's not controlled by this argument. Yeah. But at long distances, the leading order approximation is indeed just super Yang-Mills. So now I'm going to play exactly the same game we had before. I'm going to take type 2B on R5 1/6 flat space, and let's do again the same thing. But now I don't have the D2 branes. What I have instead is a D3 brane. So it was before a point particle. So this was the 6-dimensional part. This was again, the P1 part. And this was the normal bundle part. But a D3 brane has 3 spatial directions, not 2. And therefore, it extends like this. What's the interpretation of this? Well, it's no longer a point particle from the perspective of the 6-dimensional theory. What is this thing? It looks like a string. String here just means anything that has like one spatial direction and it moves forward in time. So we're literally imagining like, a circle that moves around. Okay. Now what is, so I should have said this over here. What's the mass of the point particle here? The mass of the point particle goes like the volume of the P1. So in the limit where the volume with P1 shrinks to 0 size, the mass goes to 0. You can do a similar thing here. For a string, you don't really characterize it by a mass, but it's something that has units of mass to some appropriate power. We have a so-called tension. And the tension goes like volume of the P1. So if I take the volume of the P1 to 0 size, this is when I get back to the massless limit and I restore the gauge invariance associated with the SUN gauge symmetry. If I do this over here, I'm getting a system that involves strings which are becoming effectively tensionless. What is the characterization of this? This is what's referred to as the AN 2-0 theory. And this is an example of a 60 SCFT. Why am I calling it an SCFT? It's clearly got local dynamics, and in a conformal field theory, basically, as I was saying before, all of the mass scales are basically either 0 or infinity. There's no intermediate mass scales. Everything is just exactly massless or infinite in mass. What's happening here? All the distance scales in the geometry are being either sent to 0 or infinity, right? There's no like finite size scales. So in that sense, this is the reason why we have this CFT here. Okay. Okay, so that's our next example. Any questions about that? Six dimensions? Oh, because of these. So this is 1 time in 5 spatial. So it's a quantum field theory that lives in 6 space-time dimensions.
Yeah, so you not only extract the P1, but also the normal.
No. The normal direction stays. I mean, the normal direction was already non-compact. Like, I don't know how to get that guy's going to be non-compact regardless of what I do.
Yeah. I mean, why don't we cut it at 8?
Oh, because the D3 brane is wrapped on this thing, right? It can't. The states that we're building here cannot wander arbitrarily off in the 8-9 direction. So every time I try to move it off in the 8-9 direction, so the 0 section of this thing is collapsing to 0 volume, right? But if I try to move it to finite volume, it's getting shrunk back down to 0 size. Yeah.
Yeah, there's one more side of work.
Yeah. Thanks. Okay. Other questions? Okay. So where are symmetries in any of this game? So before I get to symmetries,
In this case, this point, does that correspond to the photon or
the D2 is more like the is more like the W boson. So if you do SU2 gauge theory, so there'll be like W plus, W minus, and then Z and minus Z. These will be the things you get from the reduction of the 3-form potential, and these will be the ones you get from the wrapped D2 branes. So in other words, these are building up, if you like, the simple roots. The -2 curves are building up for you the simple roots, and we're literally building the generators associated with the E alphas of that Lie algebra. Yeah. Okay. So I haven't said anything too much about symmetries in this setting. Probably going to regret this. I already regret putting this on the one that doesn't move. But all right. Anyway, it's all right. Okay. So. Yes. Well, maybe it's good because I'll keep coming back to this example. Okay, so here was the picture we had in general. And what I want to do is get some characterization of symmetries in the setting. And so I'm going to first give you kind of an indirect way to access the symmetries, and then we'll explain like a more direct way to go and look at them. So the more indirect way, which is historically, which came first, at least at the level of string theory constructions, is to talk about so-called heavy defects. Heavy states. In the context of an SCFT or a CFT where everything is either massless or infinitely massive, these things will formally have infinite mass or infinite tension. So here's our picture again. I'm going to assume that I have, again, this kind of conical geometry like this with some singularity. So X is the whole thing, and then there's some boundary off here. And what we're going to do, like we did with the -2 curves getting resolved, so we had this picture, where we start with C2 mod Zn, and then, we resolve it in some way. We're going to consider what would happen if we did like a little resolution over here. So I'll write it like this. X is, for example, C2 mod Zn, or C3 mod Zn, or one of those. So we're imagining that the full space-time is going to look like R, some d-dimensional quantum field theory times X. And we're going to take 2A or 2B or M theory on something like this. Okay. But we're going to assume that X has some singularities. Why? Because we want to have an interesting quantum field theory stuck at the tip of the cone. Okay, and then we're going to consider, okay, let's imagine doing some resolution like that. Okay, so I want to build not necessarily interacting degrees of freedom, but I want to kind of probe those interacting degrees of freedom by putting heavy objects into the system. So how am I going to build you heavy objects? So let's consider again X equals C2 mod Zn. The boundary is just some lens space. And okay, as you all know, the H1 is just pure torsion. So let's take a look at what we're doing from the perspective of 2A and 2B, our two friends that we talked about before. I'll put 2A here. And I'll put 2B here. Now, I'm going to change what I meant by 6, 7, and 8, 9. So previously, 6, 7, 8, 9. So previously, 6, 7, and 8, 9 were parameterizing a P1 and a normal direction. Well, what I'm going to do instead is try to respect more of this boundary topology that I have involving boundary X. So I'm going to instead write X as a cone over S3 mod Z. Okay. So in other words, there is a radial direction R like this. So asymptotically, everybody is going to look as if it's just the 3-sphere sweeping in. Something is going to happen to the metric if I've blown up near the tip of the cone. But asymptotically, as I approach the large radius limit, it'll be described by this cone. So what I'm going to do is call the radial direction R, and I'll call these three directions now the S3 mod Zn. And I'll do the same thing over here. S3 mod Zn. And my goal here is to produce an infinitely heavy or infinitely massive state. So how am I going to do that? I'm going to have it, again, fill time. And now what I'm going to do is let it extend radially. So this will be either a D2 in the 2A context or a D3 in the 2B context. What we're going to imagine is that it fills that radial direction. So it's extending all the way from the tip of the cone out to infinity. Now this is a D2 brane, so it has two spatial directions. So I still have one more that I can talk about. I'm going to wrap it over the torsion 1 cycle off at the boundary S3. Okay. So if you like, what the D2 brane is wrapping is on a cone of torsion 1 cycle inside of H1 S3 mod Z. So I claim that this is a very heavy point particle that we've just introduced into the system. How come it's so heavy? Well, the volume of the thing is clearly infinite because it's extended along this radial direction like this. So it's on a non-compact subspace, and any conceivable metric compatible with what we're writing down here is going to be non-compact. So it's infinite volume and it has infinite mass. Okay, I'm going to do the same thing for the D3 group. So this is some heavy particle. Or better yet, I can describe this as a line. So it just kind of sits there. It doesn't fluctuate, in other words. So before, if we talk about the world volume of an electron, it can jiggle around in various ways. This thing is very heavy. It just sits there as an actual line inside of the space-time. Let's do the same thing for 2B. This would be a heavy string or a high tension string. Or a surface. So I did exactly the same thing. I said, let's wrap it on the cone associated with the torsion 1 cycle. And now it's filling out the 0 direction and the 1 direction. Okay. Yeah.
How do you know that the gradients on the slide shrink along?
How do I know it's stabilized? What do you mean?
Because I can imagine, the way wrapping around the cone, but slides towards the single layer.
No, I don't think so. Because it's already filling the entire radial direction. So we're really imagining that we kind of like hold it off at infinity, if you like. So. Yeah.
You have n quantities, each one of us.
Yeah. I have n possible choices. Yes. That's it. Okay. Is that okay? All right. So now I've introduced some defects, some heavy defects. And one thing we get asked is there any way for us to characterize symmetries which act upon those defects? And indeed there is. But to get there, what we're going to do is we're going to look at, so this is there's a distinction to be made between like different kinds of defects that we've introduced into the system. Okay, so I'll refer to this as, so in physical terms, this is called screening. And it's something, the term, at least in this context, is referred to as what's called a defect group. And so there's two kinds of things that can happen when we have like an extended operator like this. One is that we have our extended object. In the quantum field theory. And it actually, you know what? Maybe I'll write it like this to avoid conflating it. This is all taking place in the 6-dimensional space-time now. It has nothing to do with the radial direction anymore. We imagine we have this thing, and it might be possible to terminate it or end it inside of the quantum field theory on a so-called dynamical state. And so we would refer to this as an endable defect. How could something like that happen? Imagine I gave you the line operator associated to the one form potential, and I have an electron in the theory. I can end the line by just having an electron stuck at the end of the line. So if there's a suitable charge state that I can find, which is able to end it, then that's what we'd refer to as an endable. So endable state. Now it could be that there does not exist such a state. And this is what we would say is not endable. Okay. So how do I characterize this in more precise terms? Well, I already told you that the dynamical states were coming from d-branes wrapped on compact cycles. And I said that the things that we're talking about here, these kinds of line operators, these extended things, these heavy defects are coming from things that are extending along the radial direction. They're non-compact. So what we want to talk about is, roughly speaking, calculating P is probably a bad name. Some M form, some M cycles. These are associated to the dynamical states, and these are associated to the defects. This provides me a way of characterizing the defects that cannot be ended by dynamical states. Okay, so these are the ones I cannot get rid of in any way by having a dynamical state in the game. Okay. Okay, maybe I'll just briefly mention about 5D CFTs, but I'll try to stick to the 2A and 2B side of the story. So there's a nice version you can tell involving C3 mod gamma. And it's essentially what you think is going to happen. We take an M2 brane. So here's the 5D space-time. And then we have, in this case, some S5 mod gamma. And you know,
yeah. Regarding SDFT, is that the C3 mod gamma has some contractible force, like
yeah, it has to have a collapsing divisor. That's right. So we have to be able to. So I resolve it. I need to have a collapsing divisor. So this is the hallmark. So similar to in 6D CFT, where you look for like strings which are collapsing to zero size. In the context of a 5D CFT, the thing you look for is again a string which is going to zero tension. Where do you get such things from? You get them from M5 branes wrapped on divisors in the resolve phase, and then you collapse them, and the tension is going to zero size. Yeah. So what we can do here is we can again consider S5 mod gamma. In general, this S5 mod gamma might have various fixed points, which is an interesting thing to look at. So for example, here at H5 S5 mod gamma is in general given by an abelianization of, well, there's some normal subgroup associated with fixed loci. And this thing gives you the one-form symmetries. You have to be a bit more careful in this case. There's another way to read this off, even for more general Calabi-Yau singularities that we worked out in the paper with Del Zotto and all. But this is, I think, good enough for today. So it's wrapping some torsion one cycle inside of this thing here, and that thing is producing the heavy defects associated with the electric one-form symmetry. And okay, you can play a similar game where you wrap M5 branes on various objects and look at the magnetic two-form symmetries you also get. Okay. I'm going to skip the discussion on two groups. So two groups are interesting, but I won't talk about them today in the interest of not going too far over. Okay, so that's at the level of talking about higher form symmetries. Now, in the context of generalized symmetries as they're being studied in quantum field theory, so this is a subject that's kind of going back to like 2014, this is actually not completely the way people characterize what's going on. So what are they talking about over there? Actually, let me remove the 5D CFT since I won't be using it very much. Okay, so this is going back to 2014, so almost 10 years ago, Cyberg and all. And the main message or the main idea is that there's a sense in which symmetries are topological. So the way I've been characterizing things so far is, well, the symmetries act in operators in various ways. So the idea is to consider a group G and O some operator in representation of G. And okay, what do I mean by that? Okay, O acts in some way, gets acted on in some way by some elements G inside of the group. Okay, so let's imagine that we had a local operator. One way for us to characterize what we're doing is in terms of, let's say we're working in a d-dimensional quantum field theory. So our space-time is d-dimensional. Let's imagine we surround the point that we're interested in, x, by some d-1 dimensional subspace. Let's imagine dragging it across this thing I'll call u sub d-1. What happens? Well, one way for me to characterize the action on the local operators is in terms of if I drag the local operator through, or better, perhaps I drag this bounding surface through it, I can cause a transformation in the operator by just moving it through. So this is the statement that it acts in this way. Now, the nice thing here is that you can immediately start generalizing. This is what we refer to as a zero form symmetry, acting on local operators. In a one form symmetry, so the notation is a little bit, I would say weird, but this is what we call this, and then G super 1. If you had a line operator, you could surround it by a D minus 2 dimensional subspace. And again, you could ask what would happen if, now for the one form symmetry, drag it through. So the point is that the dimension counting is dictated by saying that these things must properly link as I pull them through one another. So in this case, everything is always the support of this thing plus the support of this thing must add up to D minus 1 in order for it to link properly.
So what is little g? Little g is
Little g is an element of the group G, of big G.
big G is a discrete group or is it?
No, it could be whatever you want. It just has to be a symmetry of your quantum field theory. So it could be a U1, for example. And it's just doing something so it just acts by some representation on it. So
what is the statement I'm saying? Like you have some separating.
right. So the thing is that I'm going to interpret this thing as a topological subspace. So this is some topological operator. Why do I call it topological? The point is that if I deform it or something like this, it doesn't really matter. It doesn't affect like what's going to happen. The only thing that matters is did I cross over it or not? So the local profile of this submanifold doesn't matter too much. I'll give you an example of how we build this thing shortly, but that's the idea. Yes.
So we're not assuming that the theory is topological.
Correct.
Right? Is it topological like locally or not?
No. So that's what's interesting about this. The quantum field theory has just got its ordinary interacting degrees of freedom. It's local. It's doing the usual things. The point is that we're going to reinterpret how symmetries are realized, or we're going to revisualize what symmetries are doing in terms of these topological operators. And they're topological in the sense that it doesn't really matter where I move them. So, there's basically some finite jump that happens when I cross through. This is the sense in which it's topological. So that's what's interesting about it. Basically, the statement is that for any quantum field theory you write down, so long as you give me a symmetry, there's a topological sector or there's a topological thing to speak about in this setting. Yeah, which is. Yes, that's right. That's right.
Of course, you have your own model. The way I think about it,
yeah. Yeah, so I'm imagining that I put the whole thing, so wherever your coil edges are, make a big ball around that. And then I'm going to drag the whole collection through. Yeah.
But is D the space-time division?
Yes.
So suppose we're in a four-dimensional Maxwell state, and this O of X is just an electron. But isn't that surrounded by, let's take a time slice, right? That's surrounded by S2 instead of S3.
Well, so no, what we're doing, well, so first of all, I don't think, okay, what we want to do is talk about, if we're talking about Maxwell theory, then it's just the field strength by itself. So like F mu nu, and that's it. There's no electron per se. And so there we would actually be talking about like line operators. And so what you're doing there is you're actually looking at the flux created by the line, by the electrons and so on. And so that's the reason why you'd be talking about a line operator and then a two sphere that's collecting that flux. Does that make sense?
Okay, what about the Planck-Orbital theory where you have a scalar field there? It's surrounded by
oh yeah, so that one, so yeah, if you take like just scalar field theory, you have a discrete zero form symmetry, sorry, a discrete Z2 zero form symmetry. Yeah. Yes.
Can I maybe respond to the question that was asked previously?
Yes.
Yeah, so in the modern view of quantum field theory, the claim is that there exist these operators which may act only on a subset, namely only the ones in the interior of that region, not necessarily on all of the operators. It doesn't mean that the theory is invariant when you act with such an operator. The claim is that the correlation function with that operator there on the left-hand side is equal to the correlation function without the operator, but where you act with by the symmetry on the operators inside of it. That's not to say that this action is going to leave everything invariant.
Like you just want to start at operator, those are inside.
Yeah, that's right. Yeah.
Which is you kind of change the description of your theory to move aside.
Sorry, you said
You kind of change the description of the theory as you move aside the ball by one.
Well, you're not changing. It's not that you're changing the description of the theories. You're inserting that operator into the pattern call. So in a sense, it's a different theory. I mean, it's a different correlated theory with that. Yeah.
Is it fair to ask, like, is it similar to like in 2D CFT, if you're like radial quantization, sometimes you construct the charges by integrating like homomorphic current around a circle, and if you want to know how it actually acts on state, you sort of pull this towards the origin. That's how you can say that, like certain things are annihilated by certain charges. Is it somehow the same idea here, or
Well, it's related in the sense that you have like okay, what's one way to build the U? It's nothing exotic in like conventional quantum field theories. You imagine that you, yeah. So for example, what would you do? You would say, okay, I want to take the charge, and usually I think about it as integrating over some spatial region of like the time-like component of the current.
Yeah.
Right.
Yeah. Okay.
It's that thing. It's that thing. So in other words, this U here, this would be like U3 in the case of that guy. And you just write, oh, I want to have it over, this D-1 dimensional subspace of J0. And we're literally just collecting all the flux within that region.
I see. Well, and as long as it's actually a symmetry, then you're allowed to pull it.
Yes. Yes. Yeah. Okay. So this is just a general set of things that you can talk about. And okay, now I really do regret putting it back there because oh no, I can do it like this. So now you could ask, okay, great. Where are so I told you this nice story about the defects. Symmetries are acted on by the defects in some way. So if I give you one of these defects and I drag it through one of these topological U's, I'm expecting some action on it. Where are these in the setup that I'm speaking about? Doesn't look like they're, or how do I construct such things? So where are the U topologicals, I'll say. Okay, so I'll write down the answer and then I'll explain why it's a good answer. Let's do it for 2A and 2B. So what we said before, 9, let's do it again. Okay, so I gave you this D2 brane. Let me split it up. So again, this is the radial direction. This is the lens space direction. And I do it again. Here's the radial direction. Here is the lens space direction. So let's take the D2 brane and let's first talk about the defect. So what I'm looking for is some kind of U, some topological thing, which when I cross it through is going to produce the phase that I want on this thing. Well, what could such a thing be? So at the level of the supergravity theory, there's a natural guess to write, which is given by integrating along the radial direction. So let's say it's wrapping the torsion one cycle or something like that. So wrapping some torsion cycle times, so it's 1, 2, 3, 4, 5, 6 directions. This is the 6th form flux. And locally, you can write that thing as D of a 5-form potential. Okay, so this is the one that acts in the appropriate way, because I say that if I want to measure the D2 brane charge, I can collect the amount of flux associated to it by integrating over G6. Okay, now if I look at this thing, and I really do interpret it as D of this thing like this, I can pull it by Stokes to somebody integrated like this. So this sigma 4, by the way, is in the QFT directions. This thing here is in the S3 torsion 1 cycle direction. So what is this thing turning into? Red is the radial direction. So we have this direction, sorry, so it's this radial direction like this. Gamma is a cycle inside of H1. And then sigma 4 is somebody that's living inside of the 6-dimensional space.
And you think it's surrounding the D2 brane as a compact, supporting a compact cycle or non-compact cycle?
The D2 brane's on a non-compact cycle, but what we're doing is we're going to put it in such a way that it links with it in the 10-dimensional space-time. So the operator which is acting on it is this integral of the flux.
So D2 brane itself, if you draw the picture, stretches out in the radial direction.
Correct. So I don't want to, so
How do these guys link?
Why is it parallel? 40 extra 40 dimensions.
They already link in the 4-dimensional, in the 6-dimensional.
right. Yeah. Right. So just one second. So we have and maybe I should put it here. So a different direction. Yeah. Yes.
So the D4 doesn't have a time direction.
Correct.
Do you want to look at the 5-dimensional or 6-dimensional?
Wait, the 4 brane needs an addition. The 4 brane.
Okay. Yes.
Why is it clear that there are n of each of these types of operators?
Because H1 of this thing is order n. H1 of this thing is the n. Perhaps a less confusing way to write it is to say, let's ask what it's doing on the dynamical states, which would link like you're asking about. But it turns out to be equivalent to just doing it straight through like this and just wrapping it, putting a D4 brane in like so. So the idea is that the thing is linking both in the quantum field theory directions and in the boundary X directions.
The gamma is actually part of D4, the 8th dimension.
So gamma is living is a 1 cycle inside of here.
Yeah, when you draw this.
Okay. Yes. So gamma, so the D4 brane is going to wrap gamma and the sigma 4. So it wraps a 4D subspace inside the quantum field theory spacetime, as well as the torsion 1 cycle in the boundary S3. And so the statement is that if I look at what the D2 brane and the D4 brane are doing, and I try to pass one around the other, then I see that I pick up a phase. That's the claim. But by the time we're done. Okay. I can do the same thing over on the 2B side. Here, D3 brane is magnetic dual to itself. So so this is again spot on exactly what I need. It's a D minus 3 equals a U, 3-dimensional support. So if I drag the string operator right through this thing, it again produces, it has the right properties to produce the shift in the phase. So this is implementing the symmetry operator. So the key point here is that it doesn't actually wrap the, it's off at infinity if you like. So the defects are being created by things that extend in the radial direction, and the U's are being created by things that only wrap the boundary cycles, which would link with the things we originally wrapped the defects on. Now, what are the properties of this thing? So precisely because it's like off at infinity, so I'm holding it there, it's off at infinity, it doesn't contribute to the local dynamics of the quantum field theory. So the only thing it can do is exert an influence topologically. It can't change any of my scattering amplitudes or anything like that. I can stick it in, and I can deform it in various ways, but precisely because it doesn't slide to the origin, the tip like that, it can't do anything to the local dynamics. Okay, so there's a topological field theory attached to this thing. What is the topological field theory? So let me just focus now on the D3 brane case. So the claim is, if I want to talk about what this U is, the topological, what I do, I want to talk about basically the topological terms of the D3 brane world volume action. So what do you path integrate over? There's a connection that you path integrate over, and you have, I'll pick a convenient normalization. So let's call the thing that the D3 brane wraps S. So S is some manifold. What does this thing look like? Okay, so since I'm dealing with torsion 1 cycles, it turns out to be more convenient to characterize the whole thing in terms of not just ordinary cohomology, but in terms of differential cohomology. So I think sure all of you know better than I do. So let me not. So roughly speaking, what is this topological term? So I'll first write down kind of the moral answer, and then I'll explain how I correct it. I get some characteristic classes showing up for the topological terms. The point is that the thing I path integrate over is these, and these other terms are basically background fields that are influenced by what I've done in the field theory of interest. So I'm getting some term like this. Now what I'm going to do is essentially, yeah.
But you're saying you're writing
the topological terms.
Topological terms in the D4 brane path integral.
Yes. The leading order term is the one we already wrote over there in the supergravity. It's integral C5. That's the leading order bit. But now that I've told you that I think it's a D brane, I'm on the hook for everything else. I'm now forced to talk about the rest of it. And so it's the connection shifted by the NS2 form. So in other words, F is this thing. Yeah. And this is the tangent bundle, and this is the normal bundle to S. Okay, so I've written down what would happen for the D3 brane. Now, okay, the statement about there's a slightly involved statement about doing the appropriate dimensional reduction. So this is the thing that lives on what? In this case, it's a 3-manifold times the torsion 1 cycle. So one of these things is a 3-manifold inside the quantum field theory, and the other one is the torsion 1 cycle. And to the quantum field theorist who doesn't know anything about torsion 1 cycle, this or that, this thing here will just show up as a way of labeling a topological operator in the quantum field theory. So there's some charge associated to that. That's the charge acting on the defect in some way. So I need to find you a way of basically writing sigma 3 times gamma. do the dimensional reduction of this thing down to a three-dimensional topological field theory. So in other words, I expand an appropriate basis of forms. The appropriate way to do this is via, well, the way we know how to do it is through differential differential cohomology, which allows us to track the torsional cycles. Rather than go through the details of that, let me just say that by the time you're done, you get a 3D TFT that live with support on sigma 3. And I'll be vague about what that one is unless you would like me to go through examples. So this is being accomplished by, expansion in this case. That's correct. That's right. That's well. So what I'm doing is I'm starting with the four-dimensional topological field theory on S, and then I do my dimensional reduction on the torsion 1 cycle. And so then by the time I'm done, I now have this 3D TFT and its action on in the purely in support in the quantum field theory directions.
You started with a much larger dimension.
Yes, but the D3 brain was only living on 2, 3, 4 and the torsion 1 cycle. So that was 4 out of the 4 out of the 10. So the topological field theory I started with is localized on this D3 brain. I do the reduction on the torsion 1 cycle, and that gives me a 3D TFT just on these 3 directions here.
Sure. I guess my question is, consider the full symmetries of your theory, then it's going to be much larger, right? E plus 1 dimensional.
Oh, sorry, that's a different thing. Yeah. So there's a symmetry TFT which controls like the global symmetries and so on.
Yeah.
You can also access that by basically starting with this thing here and doing a dimensional reduction of S3 mod Zn. And then the TFT you're talking about is the one coming from these 6 plus the radial direction, where the 6-dimensional theory is viewed as kind of like an edge mode or a state in that 7-dimensional TFT. Yeah. So I'm not talking about that directly, but of course there's a nice relationship with that one for sure. Yeah. Okay, so since I yes.
C0, C2, C4, these are like fields, and the curly F are also
C0, C2, and C4 are the C's that I talked about over here. So in other words, if somebody gave you a non-trivial Chern class or one of these things, you'd be saying, I induced some lower dimensional brain on the world volume of the D3 brain, something like this. That's the physical interpretation of saying.
Those are differential forms with C0, C2, form.
Yeah. So okay, if you want to be more precise, I'm doing the pullback. So those guys live in the bulk, the 10D. I'm pulling them back onto the world volume associated with S.
And the curly F is
Curly F. So there's a. Sorry. Yeah. So curly F is. Oh, did I erase it? Oh, I'm sorry. Yeah. F is a usual curvature associated with this thing here. Yes, you have a gauge field on the D3 brain. Then you have a shifting by the B field. And the B field is again one of these bulk 2 forms that we pull back onto the world volume. Okay, so the general statement now is I now have a machine to produce for you a topological field theory associated to each of the symmetry operators we're talking about. There's a leading order approximation just given by, starting with this thing here, but I can recognize now physically that, oh, this is just the leading order to a more exact statement involving actually a whole topological field theory coming in here. Now,
so where's the leading order term here?
Sorry, where's the what?
Where's the leading order term?
C4. C4 would have been the leading order term. So it's a top degree thing. So everybody else is just 1.
Yeah, you did that to it. Okay.
Oh, sorry. Sorry, this is over in 2B. Yeah. Yeah, I'm doing the more interesting case now. But okay, so now you can do more. Okay, so what can you do with this now? So now I've given you this thing that's a more general kind of symmetry operator. And now you can ask, well, what would happen if I start looking at what it does in interesting quantum field theories? One thing you can do is not necessarily, or not exactly the examples I talked about already with the 2-0 theories, C2 mod Zn. You can do it more generally. You can talk about any 6D theory. It turns out that all known 6D CFTs can be characterized in terms of canonical singularities inside of a non-compact elliptically fibered Calabi-Yau threefold. So let's write it like this. They have actually a very simple characterization, at least parts of it do. So let's call this our Calabi-Yau threefold. Okay, I'm sorry to abuse notation. Just roughly it looks like this. And the defects that you talk about are actually associated to boundary B and then cone of B. So in F-theory world, this is kind of some auxiliary device that we use to parameterize the background, but the 10-dimensional spacetime just makes reference to B is some complex twofold, which is non-compact. Okay. Turns out that you can do a similar thing where you look at these different kinds of bases, and what you can do is you can ask what kind of time.
I thought you told me today that there are 60 little string theories with 1-0 supersymmetry.
Yes.
But if you take the conformal limit, then you get back to 2-0.
So some of them become 2-0 and some of them stay 1-0 CFTs.
So they're asking non-trivial 1-0. So
absolutely.
Some of them have non-trivial conformal.
Yeah, absolutely. So there's plenty of 1,0 little string theories that go to 1-0 CFTs, for sure. Yeah, and they're all engineered in this kind of way. Yeah. So what you can do is you can ask about D3 branes wrapping cones of torsion 1 cycles in this setup, and you can start turning the crank and asking what kind of topological field theory do I get when I do that. One of the interesting things that happens now is that you actually discover that even though the thing we started with was some symmetry group like this, if you consider, okay, so I'll be extra vague here. If you consider bringing 2 of these topological operators together, so they're going to be supported at the same location in the spacetime, but we'll give them different torsional charges and different values of those kind of things. It turns out that what you get is not just another one. It's no longer a group-like structure. You get a more general fusion rule. Which looks like, okay, maybe to avoid or to lead the discussion a little bit, what you get is a summation on other symmetry operators, but multiplied by more general coefficients. Let's see how to write TABC. These things themselves are usually, 2D TFTs of various kinds. So in other words, the fusion rule that you get is some kind of more general product like this. How can we deduce something like, or how do I know that that's what's going to happen? Well, I literally just take this thing. I have an explicit expression here for what the path integral is supposed to be. Take this thing here, take this thing here, multiply them together. It turns out that when you do the path integral, you can repackage it in terms of a sum like this. Okay, so the usual group-like statement is just that there's a single term here, but what's actually happening in more general settings is that you get what are called, okay, the name that is given in the physics literature is called a non-invertible symmetries, and the reason is it's, if I write down like U dagger, usually we'd say U times U dagger is identity, but even for U times U dagger, it turns out that the sum is not just a single thing. It turns out that it's often a more general, sum over TFTs like this. It's just labeling the different choices. So in the particular case I'm talking about earlier, it would just be the torsion 1 cycles. That would be the labeling. So just the elements of H1. Oh, that's some topological field theory in 2 dimensions, typically. It's another one of these path integrals, but now over a 2-dimensional subspace.
So if you were to start with string theory, right? We know explicitly theory along with the 4 branes, 80 singularities. So you're just putting these things together.
Exactly.
Okay, but why do you get a non-trivial sum as opposed to just some kind of correspondence between UN and 2K theory with UN plus K. It depends for those details.
Right. So another way of saying this is that when you do, okay, so there's a picture that is not due to us. So what we did is we just did the straight QFT statement, like do the dimensional reduction just to the level of here's the topological operator, follow your nose through and multiply, and what you'll get is this fusion rule. Now, from a string theory perspective, you can ask a very similar question, and a nice case was worked out by okay, I'm going to forget some of the authors: Abruzzi, Bob, Bonetti, Schaefer, Nemecki, and a lot of people on the paper. Anyway, so the point is that what they did is they looked at what you might think is the simplest case, U and U dagger, and multiply those two together, right? What would that correspond to in string theory terms? Well, that corresponds to a brane with an anti-brane. So take like a D brane and take an anti-D brane. What happens if I multiply them together? Well, if I switch on various background fields, there's no guarantee that it just annihilates the pure vacuum. You can get lower dimensional objects stuck on the brane. That's this stuff. So those lower dimensional objects are those things that are getting spit out. Absolutely. And so that depends on the quantum field theory in under consideration. So sometimes, yeah, it's just an ordinary group-like law as you expect. But the point is that there's no guarantee that it will be group-like. A priori, you should actually expect it to be this more general structure. Okay. I don't know. In the interest of time, okay, I can keep talking. Like what we're doing now is basically applying the same kind of technology in different kinds of quantum field theories, looking at different kinds of branes, just asking what are all the different kinds of fusion rules you can write down. Sometimes there's mixing between these things. Something I didn't talk about today is you can have 0 forms, 1 forms, but then the 0 form symmetries can also act upon the line operators. You can get more general 2-group structures that will mix the two. They can kind of extend further. You could ask what would happen if the 2 groups started to fuse in non-trivial ways. All of that stuff can happen. It's not worked out completely. Usually people just take simple examples and play with those, but the string theory perspective suggests that they all kind of get mixed together in an interesting way. So that's one thing we're looking at. So let me just give a couple summary and some conclusions, and then I'll stop. So those are things I didn't talk about. So let me just sum up now. Conclusions. Okay, what did I tell you about? So the general picture is basically all contained in this thing here. We have heavy defects, and they fill the radial direction. The topological defects are at infinity. Talked about fusion. Now, one thing that I didn't talk about, because we don't really understand how it works too well, is that, of course, if you wanted to talk about, a nice way to characterize D-branes, usually we think about it in terms of being, elements inside of some derived category of coherent sheaves, some bounded derived category of coherent sheaves. So you could ask, how does that fit with this picture? And the answer is, I don't know. I suspect that it does in some interesting way, but I don't understand, for example, how the fusion rules that we have over here would fit with that sort of story. So somehow I want to attach a topological field theory to each one of these, complexes that I usually have in derived category, but I don't exactly see how these kind of explicit formulas would come out from that perspective. Another very natural question is how would mirror symmetry work with this kind of thing? I don't know. Presumably they have to spit out the same answer for the quantum field theory, but the precise way in which that happens, I'm not sure. Anyway, there's lots of other questions you can ask both on the physics and the math side, but I'll stop here. So thanks.
So among the defects you include, some of them will preserve formal invariance.
Yeah.
Many will just break apart.
Yeah.
Did you distinguish between those, or here you're just purely look at the blood, so you don't really regard that?
Yeah, at this level of analysis, it didn't matter too much, whether it violates conformal symmetry and so on. Yeah. So. Yeah.
I just one clear question. you extend your derived category, like in some G,
Yeah,
I mean, in this story, right, all you're doing is truly topological, so you're not going to see any derived category stuff at all. You're just going to see K theory.
right,
yeah,
but
you
but.
extend by that K theory and stuff, meaningful way.
Yeah, but I suspect there's more going on. For example, with the brain anti-brain annihilation, that starts to suggest that you really do want to kind of like track like all the terms in the complex rather than just saying like, oh, there was a K theory charge that came out. But I'm not sure.
If there's no more questions, thank the speaker.
You think?